So welcome everyone to today's webinar on building a smarter hospital, how tracking surgical items with RFID is being used to save money, time, and lives. My name is Justina Valencia, and I'm part of the marketing group at JDAC North America. On the line, we also have our presenter, applications engineer, John Gerard. Today's agenda will consist of a quick intro to JDAC and our presenter, followed by a brief discussion on what are retained surgical items, the benefits of RFID-enabled instruments and other items, understanding the basics of RFID, and how to get started with it. We'll conclude the webinar with a Q&A session after the presentation for those of you who have any questions about today's topic. We encourage you to type any questions you may have into the Q&A window located on your right. To the right of your screen during the webinar, so I can read your questions out loud to John once he has finished his presentation. Please be sure you are typing your questions to the host, which is me, Justina Valencia. We'll do our best to answer all your questions. However, if time runs out, we will email you back the answers to your questions. Next slide, please. So a little about JDAC and why we're an expert on this topic. JDAC is a business unit of Novanta. We specialize in machine vision, RFID, barcode, printing, and computing products, providing both off-the-shelf and optimized product solutions for medical device manufacturers. We're the first to implement embedded machine vision solutions into medical devices such as clinical analyzers, surgical machines, assay readers, and more. Our expertise is in healthcare. In fact, about 90% of our business is with medical device manufacturers. So almost any scanner in the medical field today, there's a good chance it's a JDAC solution. We're the #1 leader of OEM imaging engines to glucose meters and portable analyzers, the #1 market leader of OEM imaging to infusion systems, #1 supplier of OEM imaging engines to the healthcare market, and #1 scanner used with patient monitors, ultrasounds, and infusion pumps. As for our fabulous speaker today, John is an applications engineer here at JDAC with a plethora of experience in application engineering, radar applications, and project management across various industries. He also holds a bachelor's in science in electrical engineering. And now, the moment you've all been waiting for, here is John to take you through the meat of the presentation. John, take it away.
Thank you, Justina. Appreciate the introduction. I want to welcome everybody. My name is John Gerard. I'm an application engineer, and I'm located in Bedford, Massachusetts, Novanta's corporate headquarters. So those who don't know what Bedford is, we're about 15 miles north of Boston. As you can tell from my accent, I'm a lifelong resident of Boston. I've been here all my life, working in different industries, as Justina mentioned. So I'm going to spend probably the next 30 minutes, and I'll split it between giving you an overview of some of the problem statement with surgically retained items. I'll go into some current workflows, and then talk a little bit about some of give you some basics on RFID technology, and then talk a little bit about some of the added value that JDAC brings to the solution space. So it was interesting when I was putting together the slide deck here. My family I live with a family of healthcare professionals. My wife works 20, 30 years at Boston Medical Center in Boston. And I told her I was doing this presentation. And when I was doing the research, I came across this article in March, USA Today. And the title is called "What Surgeons Leave Behind." I thought, what a perfect way to introduce the topic to you, talking about items that surgeons would leave behind unintentionally in the body. When we would call these never events. So they should never occur. We should never leave unintended items in the body. Now, there are things like screws and things like that that are intended to leave, that are left in the body intentionally. But there are a classification of items that when the surgery is done, the item should not be there. And there's a lot of classifications of items. The first one, and let's see if you can see my little cursor here. There you go. Surgical sponges. So they tend to use a lot of sponges during surgery to kind of pack the wound area, to open up the field of view for the surgeon. Then you have surgical instruments. So these would be instruments that are used by the surgeon during surgery. And last talks a lot about surgical needles. So these are needles that are used during suturing, closing the wound up. And we call these, again, it's called, the industry term is called retained surgical items, or you might even hear it as RSI. So let's go over some numbers. So here in the US alone, we have about 6,000 operating rooms. And I mentioned earlier that if you looked at the USA Today article of surgical sponges, so typical surgery will use between, say, 200 to 400 sponges. It can also be as little as 4 or 5 sponges. And then if you look at the number of instruments that are present during the procedure, it can be upwards of 200 instruments. Now these may not all be used, but they're present. They're either on the Mayo table or they're on the back table, but these are items that are present during the procedure. And look at the number of cases here alone in the US. We have over 2,000 cases of reported cases of RSI here in the US alone. The Mayo Clinic reports that out of every 6,000 operations, there's at least one RSI case reported. And my cursor here, there we go. And if you look at the cost to our healthcare system, this is a $2 billion cost here alone in the US to our healthcare system. A retained item typically is going to cause you to have a second surgery to remove that item from the body. So traditional ways of tracking items in the body is called the surgical count. And the surgical count could be done by a surgical tech, or could be done by an RN. And it could be kept on a whiteboard, or it could be kept on a host system. But essentially what you're doing is you're counting in every single instrument, every single sponge, every single needle. You count it in during the procedure, and then when the procedure's over, you count it out. And today it could be a manual process, but the idea is that you don't close until the count is correct. So what happens when you have the count incorrect? It typically can take 20 to 30 minutes to rectify an incorrect count. And this is time where the surgeon wants to close the patient, but you can't close until the count is rectified. So let's look at some workflows in a second. But what I wanted to show you first is some data that even when we say the count is correct, in the majority of the cases where there's a retained item, the count has been called correct by the surgical tech or by the RN that's doing the counting. The number one retained item turns out to be sponges. As I recall, there's about 200 to 400 sponges that can be used during a procedure. Majority of the retained items, in this case about 60 to 70% of retained items, happen to be sponges. What's interesting is in 80% of the cases, the count has been called correct, meaning you counted in 200 sponges, and at the end, they counted out 200 sponges. So the count was correct. So obviously when the count is correct, you close. And in that case, something was left in the body unintended. And another classification is the count is incorrect. So you say, well, if the count is incorrect, why did they close? Well, there's a lot of reasons why. What will happen when the count is incorrect, they'll call for an X-ray. The surgeon will look at an X-ray, and he'll either look at the X-ray, either misinterpret it because he's not trained in imagery, or there wasn't a trained radiologist around to look at the X-ray. So the surgeon just looked at it, had an incorrect profile. And you have to keep in mind, especially with sponges, even with an X-ray, they sometimes are very difficult to detect in the body. So the count is incorrect. They do an X-ray. They call it incorrect. Surgeon doesn't see anything. He says, go ahead and close. So that's a case where there was a sponge in the body and they just happened to miss it. Now, it could be he didn't see it. So just because the count is incorrect, you still haven't proven the count is correct. So in some cases, they may not even close until the count is actually correct. So let's look a little bit at some of the workflows and how we can improve the workflows. So going from a traditional, just a manual count approach, what can you do to improve the workflow to actually get the correct count faster? So one of the adoption has been adding we call it a data matrix, but a 2D barcode. And when you open the sponges, these are surgical sponges. They come in packs of, say, 5 or 10. You can see here, there's a barcode on this label here. So they know when they're counting them in, they're going to say it's a pack of 10. And then each barcode is going to have what's called a textile barcode. So this is a barcode that's applied and meant to go on textiles. And think of these barcodes as very similar to what you have in the supermarket when you go shopping. The only difference is instead of having a paper label, this is actually a textile label. And then you would hand scan this into a scanner. So in this case here, the nurse is presenting this pack of sponges to a host system or a barcode scanner, and it counts them as it goes in. And then each individual sponge also has to be presented to the scanner. Now, in the event that the count is incorrect, the sponges come with this radiopaque marker. So if you were to X-ray a sponge, you just would be invisible. You wouldn't see it on an X-ray. So they embed this marker in there so that you can it'll actually show up in an X-ray, or it's supposed to show up in an X-ray if you have the right imagery. And this improves the flow quite a bit. So instead of manually counting, now you have a little bit better procedure and workflow, because now the barcode is keeping track of the counts. Instead of doing it on a whiteboard, you're doing it on a host system like this. There are some challenges still to this. A barcode is going to require line of sight. So you literally, either the camera or the laser, usually it's a camera, has to look at the barcode and be able to visually decode that. It's one at a time, so every pack has to be scanned in, every sponge has to be scanned in individually. Now, think about the opposite. When you're closing, the sponges are going to be covered in blood and body fluids, so it exposes the nurse to some of these fluids. And then if you've left the sponge inside of the patient, there's no way of detecting it. A barcode reader can't read through the flesh and detect the sponge inside a patient. So how do we take it to the next level? So I would call this a smart sponge, in that what we're doing here is we are embedding, think of it as like a tag. We call them tags, but think of it as like a radio transmitter inside the sponge that not only can basically talk to an electronic reader. So instead of having a barcode here, we're replacing it with an RFID tag. So what that enables us to do is I don't have to individually present the barcode to a reader. Here, instead, I've had a tag. I can wave a wand, on this first case, wave a wand over a whole series of sponges. It could be several hundred sponges, and read them all at once. So I get a really fast count. And then when if I'm looking for sponges, I can quickly locate it. I don't need line of sight, again, to locate that. Don't have to touch the sponges. I can just wave over the sponge and help locate it. It also has an added benefit, is that I can actually now read through the body to detect if the sponge has been left inside the body. Now keep in mind that 90% of the time is counting in and counting out, and less time is spent reading through the body. Because without RFID, what would happen here is the doctor or the surgeon would call for an X-ray, and you would take an X-ray, but you're exposing the patient to an extra radiation here. So if you have the ability just to read it, and realize it's left in the body, or under a towel, or under the covers here, that would save you from having to take an X-ray. But keep in mind that detecting inside is real important, but also locating sponges that aren't in the body is also equally important, and that's where 90% of the time is spent. So we talked a little bit about sponges, but also surgical instruments are a major part of this. As I mentioned, there's like 100 to 200 instruments that are used during a surgery. Some of these instruments may never get used. Some of them will sit on what's called the back table and will only be pulled up into the Mayo table unless the surgeon calls for it. So you have lots of instruments that have to be accounted for. Whether they're used or not, they're still part of the count. So what we're doing here is we're, slightly different setup. We're attaching an RFID tag to a metal object. In this case, it's an instrument of some sort. we have the ability to do really fast reads, just like barcodes. What I can do is the nurse here can grab a fistful of surgical objects, wave them in front of a scanner here, and quickly count all the instruments. You also have the ability to quickly locate items. Just like we do on sponges, you can actually move an antenna or reader around the OR, trying to locate all your instruments. Now, what I didn't talk about before, and also we also have the ability to read through the body. So just similar benefits that we have with sponges, but what I didn't talk about earlier was not only can we read and detect, but we also can transfer information to the tag. So unlike a barcode, where a barcode is just a label that you read, a tag, we call these tags, these things that are attached to the instruments, can also store information. They have memory chips on them. And one of the things that's very interesting is that when the procedure is over with, the instruments will go to the sterile processing department. And their job is to clean the instruments and get them ready for the next procedure. So there's lots of different techniques depending on the object or the instrument on how it's supposed to be sterilized. So what we can do is we can track, and this is showing instruments go, oops, I'm sorry, I went the wrong way. My bad. You can track the instruments when they're sterilized, how they're sterilized. Each instrument has a manufacturer recommendation how that instrument's supposed to be sterilized. And we can track that information. We can say who sterilized it, when it was sterilized, and how it was sterilized, and write that information onto the tag and track that. And then what happens is once the instruments are cleaned, then they're going to get kitted up for the next procedure. So these kits contain hundreds of instruments. So you want to make sure as you're kitting these instruments, do I have all the instruments in the kit? Are there any damaged instruments and are there any recall instruments? So basically, what is the status of that instrument before it leaves the sterilization processing department and heads back to the operating room? And of course, along all of this, we have software that tracks and manages where these instruments are at any point in time in the hospital. So it's the benefit of not only just detecting, but also to be able to track information about the status of an item inside the hospital. So a little bit, go over some benefits and benefits versus the barcode versus the RFID. As I mentioned, the line of sight. So that's probably the major benefit is the line of sight. You literally have to see the barcode versus I can wave a wand over or close or near to the tag itself. So it's a bit more automated. So I don't have to hand present it in front of a reader. And one other thing I mentioned too, when you barcode something, typically the read distance has to be within the field of view of the camera. And that could be anywhere from 12 inches to say 6 inches or 4 inches, depending on the type of system you're using. So here, you don't have that requirement. You just have to be within range of the antenna. And I could read hundreds of items at once, not one at a time. And I have the ability to store information, as I talked about tracking and the status of an object. And this comes really handy for applications where you're concerned about counterfeiting and security. So I have the ability to lock a tag. So once I've used it, I can say lock it, and only the host can unlock it, or even kill a tag to say take this item out of circulation, either by locking or killing it. That also works as well for counterfeiting. So if you have a reagent application and you don't want someone else, once the reagent's done, you want to throw that out. You want to protect counterfeit reagent entering that cassette. You can put a kill or a lock on that tag so the host system can't read it. Excellent. So we've been through the problem statement, talking about in the operating room some of the challenges and the workflows. What I want to then talk a little bit about for the people who aren't familiar with RFID, just go over the major components of an RFID system. So there's two types of RFIDs, in my mind. There's two types of RFID. We have what's called inductive coupling. So think of inductive coupling. Let me get my cursor here. There it goes. Okay, inductive coupling. So this one on the left here. Inductive coupling. Think of it as like two magnets. When you put two magnets together, the field gets stronger. You pull them apart, and the magnets just come apart. and you have a reader here, and you have a tag. So the tag is, think of the tag as the barcode, but it contains information that I can read, but also it contains information that I can write to. That works on the like magnetic field. Think of like Apple Pay. That would be considered like a near-field application. Sometimes people will refer to it as tap and go. And we'll see in hospital applications, we'll see two types of near-field column frequencies. We have LF and HF, low frequency and high frequencies, and they just operate in different bands. Contrast that to a RF coupling, and this is using radio waves to actually transmit and read and write information to the tag. And if you look on the left and the right, you'll see, and what's interesting is, and I know you guys will all go back to your office or go look at these tags, but you look at the tags, you'll see, how do I know what type I have? If you don't know, you can sometimes look at the inlay. The inlay, an inductive coupling will have a coil because it's creating magnetic current through their coil. And RF tags will have, like we call it, the dog bone. It'll have something that looks something like this, and it's different. It varies depending on the application and the tag manufacturer. But this propagates radio waves, so it allows me to have longer range detecting further away, whereas the lower frequency or the inductive coupling tends to be much closer, within the range of centimeters. And we operate in a band of frequencies. Here in the US, we operate at 902 to 826. So we have 26 megahertz of bandwidth. In the EU, it's less than half that. In the EU, it's 865 to 876.6. So you have about 11 megahertz of bandwidth. So you have to be concerned about, if you're shipping some unit to a particular region, be aware that UHF has is based on the region that you're in. You're restricted to a frequency range, whereas LF and HF doesn't have that. It's worldwide. And then contrasting the technologies a bit further, we talked a little bit about HF, it's short range, UHF is longer range. There are applications where HF is just a better choice, especially around liquids and fluids. It can read through the body, whereas UHF cannot read through the body. And the other thing to keep in mind is that there is, if you're reading a large tag population, let's say you got to read a couple hundred or even some cases 1,000 items, UHF protocol has schemes built in to handle large tag populations. A typical application HF won't read, or it's challenging to read a lot of items all at once. It's typically what I would see is a test tube or something being presented, or the antenna. In the application I showed you, if I go back several slides, let's see, I'll do that just for the sake of, you see the antenna here, right? So this antenna, the diameter of that antenna is going to dictate your read range for this is an HF antenna, or it could be an LF antenna. But the diameter of that antenna is about the distance you're going to read. So think of that. So the size of my read range is going to be the size of my antenna. Whereas HF, that's not the case. So just keep that in mind, that I can get larger distances, but HF I can read through the body. But again, it's restricted. It's just restricted in range of how far I can read away from that antenna. An RFID system is going to be made up of a host system. This could be something as simple as a PC, a network processor, a microcontroller, and then it's going to have application software. And then application software has to talk to a reader, and we call that an API, or an application programming interface, to be able to read and write commands to the reader. What do you want to do? Do you want to read information? Do you want to write information? Then you have an antenna. Of course, you have the reader here, and then attached to the reader, you have multiple antennas. And these all matter. Even the cable that's attached to the antenna matters. And then you have the tag information over here. And unlike a barcode, I can read the information. So this, again, think of this as like we call this the EPC, the electronic product code. This is just like, hey, I am a can of soup, and I'm Campbell's soup, and I'm chicken soup. So it's identifying a unique information about that product or item that the tag sits on. But what's nice is I can not only read, but I also could write information. There's additional memory in here that I can store whatever I want in there. Whether you want to do some type of error checking, or you want to do some type of security scheme, And you have the ability to lock, and I'm showing just a few of the commands. I can lock the tag, so meaning I can just lock memory, or I can lock the tag, or I can kill the tag. And then we communicate, both technologies communicate what's called an air protocol. So in the HF technologies, we have a protocol called 15693, and we have a protocol called 14442. The 14442 is we call it, remember, the near field tap goes really meant to read really close, from 0 to 4 centimeters. The other protocol, the 15693, can read a bit further, more like 8 to 10 centimeters, even further, depending on the antenna and the amount of power you put through the antenna coil. For UHF, we have what's called the Gen 2 protocol. The 18,000 standard has the Gen 2 protocol. Again, you have to understand the tag you're using, the protocol you're using, the antenna, the reader. It all matters. And this is kind of where I wanted to show you where we come in. Is one of the things you typically need to do is partner with somebody to help you understand these different components. In our case here, we give you the Mercury API. So these are software engineers who take these, call it like widgets, and put it into their code, and they immediately can send commands to our reader to go off and interrogate a tag. Maybe it's to increase the power, lower the power, whatever it may be, can be done. The host will talk to the API. We also have a program called RainStream that basically is an application layer that, think of it like Internet of Things. This is exactly how RFID technology is moving towards a cloud-based application where you're reading lots of tags and storing that information, sending it to a cloud. RainStream is just an application with different protocols that allow you to talk to the internet and store information. You take that a step further, we can actually, if you use one of the finished readers from JDAC, we actually, and this could be a Sargus reader, and I'll go over this in a minute. We also have a 4-port reader called the IZAR. You can embed programs. So you can have the embedded GNU compiler with the software development kits and write on-reader programs. It's simple. You could even do a Perl script, or you could do any type of Linux command on the reader itself, along with any type of JavaScript program, and compile and run those without having a host system. So basically, I remove that host system if you didn't have one, or if, an example, if you want to accelerate your development. So you know you're going to go to a finished reader, or so you're going to go to a module-based or an embedded reader. You could at least start here, write all your software on a reader like this, and then it will transfer it right directly to some of our modules. So how would I get started with all this technology? So where do I go? So hopefully you call us and we get started. We give you some guidelines and directions. We have lots of relationships with antenna manufacturers as well as the tag manufacturers, and they all matter. You want to make sure that you select a reader that's not going to read proprietary protocols, right? So there are proprietary protocols out there. You want to make sure that you're reading or you're picking a protocol that's an IEEE standard, like the Gen 2, like the 15693 protocol. So you give us a call, and then you decide, well, I'm not sure where I'm going to go. Am I going to be an embedded solution or not embedded solution? Is it going to be HF or UHF? But we can cover both the spectrum. So whether it's an embedded reader, so these are showing the HF embedded readers. We call this the M2 up here, can do both protocols. The little one that looks like a watch dial here, that only does the near field protocol, the 14442, and then we have, I'm sorry, this does the 15693, so a little bit further away. The Gemini does the near field one, so that's like the tap and go. And then we have a whole family of UHF modules that can, depending on your application, how much power do you need, what's the size restriction, how many antenna ports you need. And then we have a family of finished readers. So this includes everything. All the software includes everything you would need except the antenna and the tag. And then we have, on the far right, we've got a dual barcode and RFID reader. So a lot of applications require our nurses or a clinician badge to be read, and that might be a barcode or it might be an RFID tag embedded in the badge. So we have a handheld device that can do both. So hopefully you call us and we guide you down this path, but we've got a lot of choices. The nice part about it is no matter which way direction you pick, we have choices and options to help you. And then once we understand where you're going to go, one of the things I then will tell you to do is go get a development kit. So what I'm showing here in the top left corner here is our latest IZAR 4-port reader. It's a great application for a medical device cabinet, say, if you know you're going to have a lot of antennas. And what I'm not showing here is it can be hooked up to the internet, but also can be hooked up to a PC like the other ones to the right here. It gives you everything. It gives you the power cord, it gives you the antenna, it gives you some sample tags. If I get my sample tag, it comes with an antenna. Everything's shown in the picture there. And then moving across to the right, I'm showing you what a module. So if one of those, if you go back here, if you go these modules here, well, how do I test those? What if I go to module solution? But I don't have any way of connecting up to those? We're going to give you a dev kit. So this little square thing is a development kit designed by JDAC, and you put your module, whether it's the micro or the nano, whatever it may be, you put it down on here, you plug it into a USB port, plug it into your PC, comes with an antenna and some tags, and you're off and running. And likewise, this is also showing the same kind of scenario with an HF reader connected to a PC. That's great, but what about software? And for the UH side, I'm showing here our universal reader. And the universal reader is a wonderful, everyone we've shown this in industry loves it. It's a nice finished piece of software that has lots of options. So what's interesting about this and why it's important is that you want to test out your system. Is it going to work? And my only question is, I don't know, I need to test. Give me your sample of what you're trying to do. I don't know if it's liquid, if it has to read metal. Set up the scenario the best you can using a development kit. Then use your universal reader to program the reader. So you're not a software guy. You're just a hardware guy, or maybe you're who knows, maybe you have no experience at all with engineering. You can hook this up, set it up, and then program to the right. It's hard to see, but to the right you can see there's a bunch of settings in here. These are all settings that the software developer would want to know how to set to control for your particular application. Here, using Universal Reader, you can test out your solution space, tweak how much power you put through the antenna, change the Gen 2, and this is UHF, changing protocol settings to see, well, I've got a large tag population. What happens if I have a small tag population? And tune it for performance. And then what I'm showing in the middle here is what's on the Sargus, as the Rainstream interface. So showing you that I can configure this up. Instead of just sending the data to Universal Reader, for example, I want to send it out to the internet. Here I'm showing I can serially send it out a USB port, or I can do TCP, IP protocols, different ways of sending the data out, streaming it to wherever you want to go. And you have the ability to format the data and what types of things go out. So not only do you just get the product information on the tag, but you might want to know what antenna, how much power was used, what the receive sensitivity was. A whole bunch of things can also be sent over the interface. Whether it's Sargus or not, you have that ability. And last, what I'm showing here is our USB Pro. This has everything, including an antenna on there. It has the ability to also, you can't see it because it's cut off, but on the top you can install a external antenna as well. So where I say is get started is figure out, is it HF, UHF, then go get a development kit, then call me or one of our application engineers to assist with setting the settings, making sure you're properly communicating and setting up the protocol. I know my best practice is always call me when you get the dev kit. I come sit with you, make sure that your setup is proper. Even if you've already set up, you want another pair of eyes and ears on your application. I'm always happy to sit down. Our application engineers are always happy to sit with you, especially on the UHF. It's a little bit more complicated. So you get a dev kit, buy a dev kit, and you should be able to get started very quickly with that. And what's nice is any software you write is backwards compatible with our modules as well as our finished readers. So to kind of summarize, we talked a lot about a lot of things, but the idea of incorporating new technology is to really get more efficiencies in our system. So we showed you how you could save time by having to read a lot of tags at once. And it also presents, you still have some mistakes, but hopefully it cuts down the number of retained items in the body because you're not relying solely on humans to count it. You're supplementing the count with technology. And you are accurately managing your inventory. So you know how many sponges were used during the procedure. You know how many instruments and where they are at any time. So you can track your inventory throughout. And also by tracking and making sure that you disinfected an instrument correctly, it's controlling bacteria and viruses that are found in hospitals. And it's getting more common now, and depending on the state where you live here in the U.S., is Congress is getting involved to actually put some of these procedures in place and make it kind of a standard practice in most operating rooms here in the U.S. So hopefully we covered in 37 minutes. Leave some time for Q&A. So Justina, if you don't mind.
Yep. Can you hear me?
I can.
Awesome. Okay. So I would just like to reiterate, if there's any questions, please direct them towards the host. That's me, Justina Valencia, so I can read your questions. One question that we have coming in is, how do you locate an item with RFID?
Oh, that's a great question. It gets asked on every engagement we're involved. A lot of customers want to know, they want to locate something down to exactly where it is. And it's with RFID, it's very difficult to do that. So a lot of times in inventory management, you'll see big portals, like merchandise moving through a portal, and it locates the direction based on the last antenna or where, like near a doorway or near a shipping doorway. But to actually locate an individual item, you typically locate with close to an antenna. Now there are in the UH side, you're seeing people use receive sensitivity. And what that is the amount of energy returned back to the readers. And the idea is the more energy received, the closer the item is. So think like Geiger counter. So it can somewhat aid in the direction of the item, but what ends up happening with UHF is the frequencies can hop around. So the receive sensitivity might be, say, it might be, I don't know, 65 dB, and next time it's 70 dB. It's jumping around because the frequencies, you're only allowed to broadcast on a frequency for a short period of time before you have to hop to a different one. So it might get you close, like more like a Geiger counter, and it will jump around. But that's kind of some of the thoughts that you see in industry is using the receive sensitivity to guide somewhat of a directional. Is it in the corner of the room or left or right, top or bottom?
Okay. Another question that just came in is it possible to do real-time location with RFID?
Yeah, again, so it's very related to what we just talked about. So by real time, it's usually wherever antenna read it. So if you've got multiple antennas, and think of like a medical device cabinet. It's a great way of doing that, is that if you got, I don't know, 8 shelves and 8 antennas, then you know that the antenna 1 is on shelf 1. You can at least locate down to a shelf at real time. So as an item goes out of range of the reader, you know that it's no longer there. So yeah, you can do real-time reading. It's just not going to locate the item.
Okay. This developer kit, does the developer kit work in EU? Please may you repeat the exact frequency of HF or UHF that can read throughout the body?
Yep. So the answer is the development kits, so it depends on which chip you use. So you want to do is, if you're in EU, get a hold of our EU apps guide. But you have to order, depending on the chip, there's one that's called for all regions for the M6E, but others you may have to order per region. So yes, the dev kits are universal in that you buy the dev kit, you just get the dev kit, and then it comes with a module. Would be, if we're selling dev kits in EU, you would get a chip that works for the EU. And then, I'm sorry, what was the second part of the question?
Repeat the exact frequency, HF or UHF, that can read through the body.
Excellent. Right. So let's go back, right? So let me go back and just, I'm more of a visual guy, so I always like to visualize things. Here you go, right? So this is the LF or HS. So LF is like, you're going to find that here in the U.S. when you get your, I just got a dog actually, and they tag it. Most likely that tag is going to be an LF tag because they're very inexpensive. The HF tags, believe it or not, tend to be a little bit more expensive, and the cheapest tags are the UHF tags. And you'd say, why is that? It's because the supply chain, like your Amazons, your Walmarts here in the U.S., in retail, use UHF tags. So they tend to be much cheaper, and there's hundreds, if not thousands, of manufacturers out there that do that. So if you're reading through the body, you're probably using an LF or an HF frequency to do that. And here they are. And this is worldwide. So here, if you're in Europe, it's still going to be in this range here. If it's HF, it's going to be 1356. If you're in Europe, I think you said, you would be at, I believe it's 865.6 to 876.6.
Awesome. Thank you very much. Another question is, can I control the amount of power coming out of a reader?
Absolutely. And it's very important on the UH side. One of the things I talked about in the universal reader is some of the settings that we had in there. And one of the settings is the amount of power. Now, let me go a little further on that in saying that here in the U.S., in Europe, and everywhere else, there's a limit to how much power. So you'll see some readers will put out a lot more power than others. But at the end of the day, you're only allowed to put 30, we call it dBms. You're only allowed to put 30 dBms to the input of an antenna, and then an additional 6, so the antenna can then boost that another 6 dBm. Essentially, you're only allowed here in the U.S. 1 watt of power at the output of the antenna. The reason why they allow you to put more power at the reader output is to adjust for cable losses. So think of every meter of cable, you're going to lose about 1 dBm. So if you've got 2 meters, you're going to lose 2 dBm. And every connector, every RF connector you have, you're going to lose about 1/10 of a dBm. So as long as that loss is less than 30, then you're okay. You can't go over 30 dBm at the input of an antenna. So yes, it's programmable. On the HF side, it's a little less important. Though typical, you're going to find that the magnetic readers tend to be between a 1/2 watt to a watt. We typically sell a 1/2 watt or less. I believe one of ours is 100 milliamps, 180 milliamps. The other one might be 500 milliamps. You'll see some readers that are in the 1 watt, 1 watt range. Those tend to be non-USB. They tend to be, industrial readers. But again, that's going to give you a little bit further distance. But yes, hopefully that answered his question.
Awesome. We have a bunch more questions to go through.
Okay, keep them going.
Is there any algorithm if I want to identify the position of the item from the reader?
Is there any algorithm? I'm not aware of an algorithm that will do that for you. I know that the intent, so again, depending on the technology, the HF readers are very close, tend to be very close to the item that you're trying to read. So a lot of times you'll see the item being presented, I'm talking about the lower frequency, in front of the item that you want to read. So it's pretty easy, pretty intuitive where the item is. In an inventory management system, you'd have to use a handheld wand to locate it. And that wand, remember we talked before, if I go back to the picture up here, this is really tedious. It's going to, I'm locked up here. It's going to be, I'll show you. It's going to be the radius of the antenna here, right? So if I go back to here, the radius of this antenna is going to dictate how far away I can read. So like a great example would be, well, why wouldn't I just use HF or LF in the OR? That's great if it's in the body, but if it's not in the body, the LF RF technologies are slower because you have to be very close to where the item is, and you may miss it. Like the surgeons, the sponges may fall on the floor, may fall under a table, may go in the trash, they may stick together. there's lots of reasons why you may miss it. Where UHF would be able to read the whole entire room. Yeah, you may not know that it's you may not be able to locate it precisely down to like a foot or a meter where it is, but at least you'll know it's not in the body. You'll be able to read it, and it's unique, so you'll know that that's the missing surgical item or sponge. And so then I'm confident that, yeah, I've located 100%. It's not in the body. It's somewhere in the room. We'll find it. Go ahead and close. So that closes the count quicker, but it won't read through the body, but it'll find those items a lot quicker than an HF solution. So no, there's no real algorithm to locate it precisely down to where it is. There's talk and discussion and research on using receive sensitivity on the UH side of things to do that, but I've yet to see someone nail that application 100%.
Okay, we have a two-part question.
Yep.
What should be used for a heavily metallic environment, and will it work for auto stock taking?
Auto stock taking. Well, okay, without knowing whether you're talking HF or UHF, what I'll say is there's specialty tags out there. So first you have to say what are you trying to do? Are you trying to read lots of items? Are you trying to just read one item? So you start there, and then you figure out, is it going to be HF or UHF? And the way I determine that is if it's a lot of liquid in the environment, perhaps I would go to an HF environment. If it's not, then I could use specialty tags that are meant to mount on metal that work with UHF. So I would start there. Look at what you're trying to do. Is there liquid involved as well as metal, or are you just trying to read metal? The one thing you have to be aware of is, especially with both technologies, but HF technology, if you've got too much metal around your antenna, what it's going to do is it's going to detune your antenna. What does that mean? It means that I'm trying to talk to the reader. I'm the tag trying to talk to the reader. I can't hear you anymore because you were no longer speaking the same language. So the antenna gets pushed off frequency a bit. And it may show up as a misread every now and then, or it may not be able to read at all. So I need to know more information about what you're trying to do, but that's why you need to consult with us. You need to look at the consumable. You need to look at the tag. You need to kind of figure out, what are you trying to do? What is the read distance? How fast do you need to read? And how far away do you need to read? Those are considerations that need to know more.
Okay. Another question is, do you have any idea about angle of arrival in UHF reader?
Angle of arrival? No, we don't report angle of arrival.
Okay. Another question is, in the U.S., is there separate radiating certification for medical in addition to FCC?
Yeah, I'm not qualified to answer that question. I know that there is, so there's modular certification for our UHF modules, meaning that we certify that these modules and readers will work with certain types of components. And I'll give you an example. Is recently I had a customer who used one of our readers, but decided they wanted to design their, in a medical application, and wanted to design their own antenna because they thought, oh, how hard could it be to design an antenna? That's great, but now he's trying to take his product to market, and you still have to get your product certified here in the U.S. And part of that certification is it goes to a lab, and they test to see, are you illegally, they'll go through it first and see, okay, you used a Thing Magic reader. It says, here's a list of antennas that you're allowed to use. Oh, you designed your own antenna. Even though the customer will say, well, it's designed to their certification, to their specification, you still have to prove here in the U.S., and I'm sure this is the case elsewhere, that antenna really is what it says it is. You don't want to say, hey, I'm a 6 dB antenna, and really you're 7 dB. So the answer is, as long as you follow the guidelines and use the components that we certified with, you should be okay.
Okay. Another person wrote, the actual tags for surgical instruments afford the sterilization without ethylene oxide.
Okay, read it slowly to me again.
Okay, hello. The actual tags for surgical instruments afford the sterilization with ethylene oxide.
Okay. Well, I don't know the answer to that question. What I'll talk a little bit about, and maybe this will help you, is during the sterilization process, there's a lot of different ways of sterilizing an instrument. It could be done with extreme heat. It could be done with gamma rays. There's a lot of different techniques to sterilize it. The harsh chemicals, so again, working with the specialty tags, there are specialty tag manufacturers out there. For example, there's one of the things that we just worked with a client, they wanted to do on dental equipment, they wanted to be able to put tags, but it goes into an autoclave that uses gamma rays. And if you try to use, even if you try to use a metal mount tag and put it into that environment, what's happening is, I talked about there's memory on those tags. What would happen in those environments is the radiation would wipe the memory or corrupt the memory on the tag. So that's an EEPROM memory on there. You would have to use, so Google search, and now you're going to find searches now quite, I don't say quite, but you could find them. The UHF tags that actually have what's called gamma ray or gamma ray memory in there. So they're gamma tags that it's kind of the best of both worlds. It takes the best of RAM and ROM. It's like it's a ferroelectric RAM, they call it, or FRAM. So just Google FRAM, UHF tags, or HF tags. HF is more, you'll see more of them. And those tags are designed to withstand, say, 1,000 times through sterilization before the tag would have to be replaced. So, you know, it's a very harsh environment. I don't know what a chemical he would use. I'd have to research that out a bit. But that's a very important point he's making is the chemicals matter. So you have to pick a tag inlay or tag manufacturer that can build a tag that can withstand the harsh chemicals that these things get sterilized in.
Okay. Are these RF devices not harmful to human and living beings exposed to it?
Yeah, it's not. There's no issue with RFID radiation per se. The other thing you got to worry about is the opposite, is interference into your environment. So for example, I worked with a client recently where we think, like, because the inductive coupling works on a magnetic field, if you've got motors and you didn't properly shield or ground those motors, if the motor's running at the same time the reader's trying to read a tag, you're going to, and that frequency resonates at 13.56, the antenna is going to pick that signal up and then and it's going to transmit that to the reader as noise. So in that application, you'd put like a ferrite bead on there that would filter out that noise so it's not seen by the reader. On the UHF side, you could run into noise where you've got multiple readers in the environment and they're talking at the same time, and you can get interference that way. But no, they're not harmful to you.
Okay, and we sort of have a three-part question here, so I'll just question those separately. How many hospitals in the U.S. or Europe use your system currently?
Boy, I honestly don't know the answer to that. The reason I say that is we're not selling the system itself, we're selling the reader. So we are selling devices to the OEMs that actually make the different readers. So I don't know offhand what the number is. I'm looking across the table at my marketing person as well. So it would be a great number to have. I just don't know that offhand.
No problem. Where do I get RFID-enabled surgical instruments? Do we sell them?
We do not sell those. Typically, so here's how the workflow would be. It would be either you buy a system from, and I'm not going to advertise there are systems out there. It's not that hard to find them. That they give you the software, they give you, the infrastructure to do that. Those items would have to be tagged. So they would have a workflow where the item would come into the hospital. Either the manufacturer would tag them for you, which probably they don't, or you would have a registration process where the instrument would come into the hospital, you would tag it and register it, and then you're good to go. And you tag it with probably, depending on the device and how the manufacturer recommends you sterilize it, it probably would have one of those FRAM tags on there of some sort. And there are going to be a variety of them because not all the instruments are all the same shape or sizes. So you may have a different varieties, types of tags, depending on the shape and size of the objects.
Okay, and I believe you already answered this, but I'm just going to go ahead and ask it. What is your current inventory of surgical instruments?
Right, we don't sell instruments.
Yep.
Yep.
Is there any other questions? Please type them into the Q&A window. I'm just going to give people a few seconds to type in.
We're just coming up on 12 here.
Yes. Okay. I don't think we have any more questions.
Yeah, everyone, thank you so much for the questions. It's great. I always appreciate questions, and I learn as well. I'm going to have to go look up what that chemical compound was.
Okay, Jen, if you can just scroll to one of the last slides that
Yeah.
our concluding slide.
Sure. Yeah. There you go.
All right, perfect. At this time, I'd like to thank everyone for attending our webinar, and a big thanks to John for his time and presentation. A recording of this session will be automatically emailed to all those who registered for the event within the next week. Just another addition that in alignment with our GDPR policy, we are unable to send the recording of this event to the European registrants. To receive the recording, email us at optin@jdactech.com indicating we have your permission to send you marketing information, or you can download this recording from our website, and there's a URL link right there. That will be available on July 25th. If any of our attendees have any further questions on RFID, or any of our other technologies, we invite you to visit our website, jdactech.com, or schedule a tech day with us by emailing us at techday@jdactech.com for a free consultation. Thank you, everyone, again, and have a great day.